Hello students, let us start with the example. Let A is equals to matrix 1 minus 1 0 3 2 3 2 1 1 2. Test whether the vector x is equals to minus 2 2 1 is an eigenvector of A. An eigenvector of A. If so, find eigenvalue. If so, find eigenvalue. Solution. See here students, this is a matrix A. We have to give an eigenvector and we have to find eigenvalue. Only eigenvalue. Okay. First we have to compute. In this type of example, we have to compute A into X. A is matrix 1 minus 1 0 2 3 2 1 1 2. This is nothing but minus 4 4 2. Here A remains. X is matrix minus 2 2 1. This is nothing but minus 4. This is nothing but minus 4 4 2. This can be written as 2 into minus 2 2 1. Okay, so this can be written as 2 into x. Okay, means what? We have get Ax is equals to lambda x. So here lambda is 2. Here lambda is 2. Lambda is eigenvalue. Hence the eigenvalue is 2. Okay. If this type of example asks, then find out, means write down Ax in the form of lambda x, where lambda is an eigenvalue. Okay. Let us see next topic, the characteristic equation. The characteristic equation. The characteristic equation. In this section, we discuss the method of finding eigenvalues of a matrix A. This is done by forming a special scalar equation called characteristic equation of A. Okay. We illustrate the method with the help of examples. Okay. First example is find the eigenvalue of the matrix A. Find the eigenvalue of a matrix A. Matrix 2 3 3 minus 6. Okay. Solution. Here we have to find lambda such that satisfy the vector equation. A minus lambda I into x is equals to 0. A minus lambda I is equals to, matrix A is 2, 3, 3 minus 6 minus lambda I, lambda matrix lambda 0, 0, lambda means lambda into identity matrix of order 2, which is equals to, this is nothing but 2 minus lambda 3, 3 lambda plus 6. Okay, so we will get A minus lambda I into X is equals to 2 minus lambda matrix 2 minus lambda 3, 3 lambda plus 6 into X. Okay, we find lambda by computing we find lambda, here say we find lambda of matrix A minus lambda I by computing determinant of A minus lambda I is equals to 0. That is determinant of 2 minus lambda 3, 3 lambda plus 6. This is equals to 2 minus lambda into lambda plus 6. Sorry, here is minus lambda minus 6. We find lambda of matrix just here A by computing this. Okay, here is 2 minus lambda minus 6. Okay, minus 9. Okay, this is equals to minus 2 lambda minus 12 plus lambda square plus 6 lambda minus 9. This is equals to 0. This is also equals to 0. Okay, which is equals to lambda square minus not 4 minus here plus 4 lambda plus 6 lambda minus 2 lambda is 4 lambda minus 19 minus 9 is minus 20, which is equals to 0. Okay, here we require multiplication minus 21 and addition is plus 4. So we choose a value plus 7 and minus 3. 7 minus 3 we get plus 4 and 7 into minus 3 we get minus 21. So factor of this quadratic equation is lambda minus 3 lambda plus 7, which is equals to 0. Therefore we get lambda is equals to 3 or lambda is equals to 7. Okay, therefore eigenvalues of A are 3 and minus 7. 3 and minus 7. Okay. Now see, for a square matrices of order higher than or equal to 3 by 3 matrices, we use the following fact about determinant of A to find values of lambda. First step is let A be a given matrix. Then let A be any echelon form of, here not A, here is U, be any echelon form of A obtained by row reduction. Next step is, suppose R is the number of row interchanges used during row reduction. Then the determinant of A is minus 1 raised to R times the product of diagonal entries u11, u22 and so on up to unn. Okay. Next is, if A is an invertible matrix, then A is equivalent to IN. Then the determinant of A is -1 raised to R times the product of diagonal entries u11, u22, unn. If A is an invertible matrix, then A is equivalent to identity matrix of order n, and determinant of A is equal to u11, u22, unn with all pivot elements. Okay, not all one. Otherwise, at least one of them is 0. Hence, product u11, u22, unn is 0. So, determinant of A is nothing but -1 raised to R into product of pivot elements in U. When A is invertible, means what? Determinant of A is not equal to 0, and determinant of A is equal to 0. Means when A is not invertible. Okay. Students, for better understanding, we will see the examples depend on this fact. Okay. First example is example 1. Compute determinant of A of the following matrices using steps described above. First matrix is A is equals to matrix 1 5 0 2 4 -1 0 -2 0. Okay. First we row reduce matrix A to U to obtain U. Okay. Here A is matrix 1 5 0 2 4 -1 0 -2 0. Okay. First row operation, we perform a first row operation R2 minus 2R1. So we will get a matrix 1 5 0 0 -6 -1. Okay, and 0 -2 0. Next we will perform a row operation. Here we require 1, so we will perform a row operation R2 upon -6. So we will get 1 5 0 0 0 1 1 upon 6. This is 0 -2 0. Here we require 0, so we will perform a row operation R2 plus 2 into R3 plus 2 into R2. So we will get matrix 1 5 0 0 R3 is -2 plus 2 1 1/6 here, -2 plus 2 is 0 0 plus 2/6 is 1/3. Okay, so we will get sorry students, don't do this step. Here we require 0, so we will perform a row operation here we require 0, so perform a row operation R3 minus 1/3 into R2. So we will get matrix 1 5 0 0 -6 -1 0 R3 minus 2, this minus minus become plus, 3 by 3, 6 by 3 is 2, so minus 2 plus 2 is 0, and here is this minus 1 into minus 1 by 3 is plus 1 by 3. So this is your matrix U. Okay, this reduction uses no row interchange operation. This reduction uses no row interchange operation. That is R is equals to 0. R means number of row interchange operations. So therefore, determinant of A is nothing but minus 1 raised to R into product of pivot elements in U. Okay, which is equals to minus 1 raised to 0. Here R is 0. Product of pivot elements 1 minus 6 into 1 by 3. This is minus. Therefore, determinant of A is equals to minus 2. Okay. Let us take next example 2. Let us take next example 2. A is equals to matrix 0 3 1 3 0 2 1 2 0. Okay. We have A is equals to 0 3 1 3 0 2 1 2 0. Okay. So we obtain a row echelon form of this matrix. So first of all, we perform a row operation. Yes, students, see here, this here is 0. That's why we perform a row operation R1 3. So we will get matrix 1 2 0 3 0 2 0 3 1. Okay. Next, perform a row operation R2 minus 3 R1. Matrix 1 2 0 3 minus 3 is 0 0 minus 2, sorry, 0 minus 6 is minus 6, and this is 0 3 1 as it is. Okay. Now perform a row operation R3 plus 1 by 3 R2. So we will get 1 2 0 0 minus 6 2 0 0 2. This is matrix U. Okay. We obtain matrix U with one interchange. Here R1 3 one interchange. So R is equals to 1. Therefore, determinant of A is equals to minus 1 raised to R. Here R is 1 into product of pivot elements 1 into minus 6 into 2. Therefore, minus 1 raised to 1 is minus 1. Minus 1 into 6 is plus 1. 6 into 2 is 12. Therefore, determinant of A is 12. Let us take third example. Take this example for homework. 3 minus 2, 1 minus 1. Find determinant of this matrix. Okay. Let us write down one theorem. Theorem is a square matrix A of order n is invertible if and only if A, the number 0, the number 0 is not eigenvalue of A, is not eigenvalue of A, and secondly determinant of A is not 0, and secondly determinant of A is not 0. A square matrix A of order n is invertible. The number 0 is not eigenvalue of A. Means what? Ax is equals to lambda x. This vector equation has no. If you solve this equation, you will not get here lambda is equals to 0 if A is invertible matrix at that time. Okay. And second is determinant of A is not 0. Okay. Now we will see definition of characteristic equation of A. Characteristic equation of A. Let A be n by n matrix. Let A be n by n matrix. The scalar equation determinant of A minus lambda I is equals to 0 is called characteristic equation of A. Okay. Note that lambda is a eigenvalue of a square matrix. Lambda is a eigenvalue of a square matrix A if and only if lambda satisfies the characteristic equation determinant of A minus lambda I is equals to 0. Okay? The equation determinant of A minus lambda I is equals to 0 is polynomial in lambda. This is polynomial in lambda. Okay. We will factorize the polynomial to obtain the eigenvalues corresponding to the given matrix A. This is we have seen in as previous examples. Okay. See here what is characteristic equation. Let A be n by n matrix. The scalar equation determinant of A minus lambda I is equals to 0 is called characteristic equation of A. Lambda is eigenvalue of a square matrix A if and only if lambda satisfies the characteristic equation determinant of A minus lambda I is equals to 0. The equation determinant A minus lambda I is equals to 0. It is a polynomial in lambda. Okay. Let us see examples. Find the characteristic polynomial. Example. Find the characteristic polynomial. Find the characteristic polynomial and eigenvalues of the following matrices. Of the following matrices. First matrix is A is equals to matrix 2 7 7 2. Okay. Solution. Okay. Here write down second matrix. A is equals to matrix 4 0 0 5 3 2 minus 2 0 2. Third, A is equals to matrix 4 minus 7 0 2 0 3 minus 4 6 0 0 3 0 0 3 minus 8, and last is 0 0 1. Okay, we have to find the characteristic polynomial and eigenvalues of this matrices. First, here this is a matrix A. What is the characteristic polynomial? Is determinant of A minus lambda I is equals to 0 is a characteristic polynomial. So first of all, we calculate determinant of A minus lambda I. So we will get, this is determinant of, okay. So A minus lambda is nothing but 2 minus lambda, matrix 2 minus lambda 7 7 2 minus lambda. So determinant of, okay, first I will write matrix A minus lambda I. So I will get 2 minus matrix 2 minus lambda 7 7 2 minus lambda. Okay. Now determinant of A minus lambda I, which is equals to 2 minus lambda into 2 minus lambda is 2 minus lambda square minus 49. Okay, this is of the form A square minus B square, and we will know that this is equals to A minus B into A plus B. So this is 2 minus lambda. This is a square of 7. So 2 minus lambda minus 7 into 2 minus lambda plus 7. So we will get this minus lambda minus 5 minus lambda minus 5 into 9 minus lambda. Okay. Therefore, determinant of A minus lambda I is equal to 0 is a characteristic polynomial. So we will get minus lambda minus 5 into 9 minus lambda is equal to 0. So we will get lambda is equals to 5 or lambda is equals to 9. Okay. So eigenvalues of A are 5 and 9. Okay. Now we will find eigenvalues of a matrix A. Similarly, first calculate A minus lambda. This is nothing but matrix 4 minus lambda 0 0 5 3 minus lambda 2 minus 2 0 2 minus lambda. Okay. Now calculate determinant of A minus lambda I is nothing but 4 minus lambda into determinant of these two are 0. So next term all are 0. So no need to calculate it. This is 4 minus lambda into 3 minus lambda into 2 minus lambda, and this is minus 0. So we will get the determinant of A minus lambda I is equals to this. Therefore, determinant of A minus lambda I is equals to 0 implies, what implies? 4 minus lambda into 3 minus lambda into 2 minus lambda is equals to 0. That implies lambda is equals to lambda is equals to 4, 3, comma 2. Lambda is equals to 4 or lambda is equals to 3, or here I will write. Okay. Therefore eigenvalues are 4, 3, 2. Therefore eigenvalues are 4, 3, 2. Okay. Now we will find out eigenvalues of this matrix. Solution. Here A minus lambda I is nothing but matrix 4 minus lambda minus 7, 0, 2, 0, 3, minus 4, 6, 0, 0. Sorry, here is 3 minus lambda. Here is 3 minus lambda minus 8, 0, 0, 0, 1. Okay. So determinant of A minus lambda I. See here students, this is a triangular matrix, and in first semester we have seen that a determinant of a triangular matrix is nothing but the product of diagonal elements. So it is product of diagonal elements. So here diagonal elements are 4 minus lambda into 3 minus lambda into 3 minus lambda into 1. Therefore the eigenvalues are, this is equals to 0, are 4, 3, 3, 1. Therefore the eigenvalues are 4, 3, 3, 1. शकते कमी. Okay students, we will stop here. Thank you.